Swayam Prabha. Digital India. Educated India.
Okay, so let's begin our discussions related to lecture number 2, which is a historical perspective of electronics. The electronics that we have today is more than 100 years old, and like any other field, it is better to gain a better insight and a perspective on electronics as of now. It's good to look at how electronics has evolved. What were the major breakthroughs or major milestones in the development of electronics. And this would help us appreciate this particular field in a better manner. We won't spend too much time, but we'll look at it briefly at how electronics started. So this was the theme of the last lecture. We said that we should view electronics as a so the theme of the last lecture was that we should view electronics as a means, as a tool for solving problems. And the reason being is that electronics enables us to achieve a very fine control over electrical form of energy. So the issue was that whenever you have a problem, you should look for an opportunity to transform that problem such that it can be solved by electronics here. All right, so this electronics that we are talking about, it sort of started with the invention of the triode in 1906. The electronics revolution that we are talking about started in 1906 with the invention of this particular device called triode. Triode meaning it has 3 electrodes. And this was a person, Lee De Forest, who's credited with the invention of the triode. And this was a revolutionary device. And let me explain in brief how this particular device worked and what its impact was. So as I said, this is a triode, so it has 3 electrodes. The 3 electrodes are enclosed in a glass tube. So the circle, let's say, represents is a schematic of the triode. So let's say it represents the glass tube. And so 3 electrodes are, one of them is cathode, the other one of them is anode, and the third terminal, which is perforated, that's why it's shown as a dotted line, which means it's a plate with holes in it. So it's called a grid. And so the idea is that, so it's a 3-terminal device and inside is vacuum. So the idea is that if you take a metal, especially a metal with low work function, and if you heat it up, then the electrons can come out of the metal through a process called thermionic emission. And so in here we have not shown the heater part. So it's assumed that there's a heater which heats up the cathode, and so the electrons can come out of this particular cathode here into the vacuum. And then there is this other plate, anode. We apply a positive potential to this particular anode. So what would happen is that these electrons which are emitted from the cathode, they will move across to the anode because of the field, and they will be collected by the anode, and then they will flow out. Right, so this would then result in a flow of current here. The current would, of course, flow from anode to cathode, being opposite to the direction of the flow of electrons here. So a current would flow if you apply a positive potential and you heat up the cathode to a sufficient temperature. The third terminal brings in interesting properties. This third is a perforated grid. So what happens is when the electrons are emitted, they can normally go through the perforated grid and reach the anode. But if you apply a negative voltage to the grid, well, this negative voltage can repel the electrons to the cathode. So what can happen is that by applying higher or lower values of grid voltage, you can control the number of electrons that reach the anode. You could even make the number of electrons which reach the anode 0 by making the grid voltage sufficiently negative. So thereby what you're able to do is that by applying a voltage to the grid, and is relatively small voltage compared to the anode voltage here. So by applying a voltage to the grid, you're able to control this particular current here. You can make the current higher or smaller by applying this particular voltage. So what we get is a property that we call as transconductance. Conductance, as all of you know, is current divided by voltage, or in a differential form the rate of change of current with respect to voltage. We call this transconductance because we have current flowing between anode and cathode, one pair of terminals. But we are talking about change in this current between one pair of terminals due to voltage applied across another pair of terminals. Vg represents the grid voltage here. So because of this, that one pair of terminal, the current flows, and the voltage is a separate pair of terminals, we use the word trans. And of course, because it's rate of change of current with voltage, we call it conductance here. So the triode exhibited a property that we call as transconductance, change in current with respect to the grid voltage here. Now, there is of course the normal conductance, the change in current due to voltage applied across the same pair of terminals. For example, the current is flowing between anode and cathode, and this is the voltage applied between anode and cathode. We are taking cathode as a common terminal or reference terminal here. So this is the normal conductance, and in this case we just call it output conductance because you'll see later we take output. If we apply some input here, we'll take output on this side here, so we call it output conductance. So what was very interesting and sort of revolutionary about the triode was not simply that it exhibited transconductance, but the transconductance was much larger than the output conductance. Under certain conditions, the transconductance was much larger than the output conductance. And this is a very strange property if you think about it, because normally you would expect that any current flowing between a pair of terminals would be quite sensitive to voltage applied across the same pair of terminals and should be less sensitive to voltage applied across some faraway terminal here, right? But this is just the opposite. The anode current is much more sensitive to grid voltage, a faraway terminal, as compared to the anode voltage itself. So that was what was very interesting about a triode, and we can take this equation and we can rearrange it to show that change in anode voltage versus change in grid voltage is much larger than 1, which basically means that if you apply an input here, a small change in grid voltage can result in a large change in anode voltage, and what we can see is an amplification process, right? So with the invention of the triode, what one could do is build an amplifier. So one applies a small, let's say a signal here, and the anode voltage is applied through this power supply, and we've connected a load. Let's say the load could be a loudspeaker and this could be a microphone. So for example, if the microphone, let's say this is the audio signal that is over here. So this audio signal, what it will do is it will modulate the electrons flowing between anode and cathode, thereby modulating the current here. And a change in current would cause a change in the voltage over here, and we can obtain an amplified voltage across the load over here. So with the triode, we are not going into the details. We'll see that later on in the course, the detailed mechanism of how amplification occurs. So what happened was that with the invention of the triode, you could amplify signals. You could take a weak signal and you could amplify it. And meaning, of course, that let's say the power in this particular signal is P in, this is the input side, and the load, let's say a loudspeaker, the power in the load is PL. So what we are saying is PL is much larger than Pn. The power delivered to the load is much larger than Pn. Of course, you may be wondering, what about the law of conservation of energy? Well, that's why we have the battery here. So the balance of the power, PL minus Pn, is supplied by the battery here. So even though it's a DC, it supplies a current which obeys the grid voltage here. So the nature of the waveform that you see here, the current flowing through this power supply is of that particular nature. It follows that. That's why the voltage across RL is also the shape of the voltage is exactly the same as this, except that voltage is much higher and the power is much higher here. So with the triode, one could build an amplifier. We could take weak signals and we could amplify it. And the immediate consequence of that was that communication was revolutionized. Take, for example, telephone. Telephone had been invented before triode. One could communicate with a telephone, but the distances over which you could communicate was limited because as the signal travels, it gets weaker. And if it becomes too weak, it gets submerged in noise and then you cannot make out what the signal is. But with the amplifier now enabled by the triode, what one could do is, after transmitting an audio signal, let's say over a certain distance, before it becomes too weak, what you do is you amplify it again and then transmit it again for a certain distance. And then before it becomes weak again, you transmit it, you amplify it again and transmit it. Thereby, you can transmit now signals thousands of kilometers. And therefore, the long distance communication was revolutionized. And along with that, for example, the radios were enabled by triode. Radio requires amplification, requires oscillators and other things. So radio or wireless communication became possible because of the invention of the triode. So communication was revolutionized. The other thing was that triode revolutionized processing of information. So this is the digital inverter that you're familiar with. The inverter, of course, takes a signal. If it is high, it makes it low. Output is low. If it's low, the output becomes high. So basically works on binary arithmetic with ones and zeros. And with a triode, for example, one will not go into the details. With a triode, one could make an inverter. The digital inverter that you see over here, one could make it with a triode. Not only that, this is a NOR gate that you're familiar with. The NOR gate one could also make with it. This is a simplified implementation of a NOR gate. One could make a NOR gate using the triode also. And the NOR gate has an interesting property that is a universal gate, meaning that whichever gate you're interested in, AND or exclusive or even an inverter, you could implement all of that using the NOR gate. So what we are saying is that with the triode, you could build any of these gates, and of course you can connect lots of gates together. And these gates, these digital gates, they work on binary numbers, and one can do addition, binary subtraction, multiplication, division, all of that we can do here. So with the triode, one could do information processing. One could process the information. And an example of that is a computer, early computer. You can see here ENIAC in 1946. And 1946, so this is a computer. And let's look at some details about this. It has some more than 17,000 vacuum tubes, 70,000 resistors, 10,000 capacitors, relays, 5 million soldered joints. And this occupied an entire room, a 30 cross 50 feet room. And it weighed 30 tons and consumed 160 kilowatts of electrical power. And it was not very reliable, almost like 50 tubes on an average, 50 vacuum tubes would burn out and they would have to be replaced. Imagine trying to find out which tube is not working and then isolating and debugging and then replacing 50 tubes a day. So the point is that with the triodes, as an example, you could do computation, not very sophisticated computation. I mean, the power in this particular computer is much less than what you hold in your hands. But you could do, it was much better than mechanical computers that were there before the invention of the triode. So you could do computation, but you could see that it was not very easy. Even to do make a relatively simpler computer, it's occupying an entire room, it's weighing 30 tons and consuming kilowatts of power, and not very reliable. So with the invention of the triode, what we had was from about 1906 for almost like 40 to 50 years, we had an era of electronics which we call as vacuum tube based electronics. It was not just triode, there were other tubes also that were invented. So it was a vacuum tube based electronics. One could do many new things and many interesting things with those vacuum tubes. But you can see using this particular example that it was not very easy to build complex circuits using vacuum tubes, because the circuits were becoming very large, very heavy, consuming lots of power, and they were not very reliable. So that's why people were out looking for a replacement for vacuum tube. Something that had the properties of a vacuum tube, but would not weigh so much, would not be of such a large size, and would consume much less power and would also be far more reliable. And that search, all of you know, resulted in the invention of the transistor in 1948 at Bell Laboratories. This is a photograph of an early prototype transistor, and these are the three scientists who are credited with the discovery, with the invention of the transistor. This is William Shockley, and this is Bardeen here, and this is Brattain. So three of them who are credited with the invention of the transistor. And whenever a new device comes in, what happens is that when transistors were invented, this is an early advertisement of a transistor where the transistor is being compared with the vacuum tube. So this photograph is showing that the vacuum tube is so large and the transistor is so small. So the interesting thing about a transistor, you're a little bit familiar with the transistor, that it also has three terminals. Let's say a bipolar transistor with base, collector, and emitter. The interesting thing about transistor is also that, let's say, the collector current flowing between collector and emitter, assume that emitter is a common terminal. So the collector current is much more sensitive to the base voltage as compared to the collector voltage. So the same property, collector current depending far more on base voltage, which meaning transconductance, as compared to collector voltage depending on the collector voltage itself, collector current depending on collector voltage itself. So that's the output conductance. So the collector current being far more sensitive to base voltage, so meaning that transconductance is much larger than output conductance, and therefore the transistor had a similar property, and the transistor was capable of providing gain also. So a transistor could do most of what a triode could do, but it was smaller, consumed less power, and was far more reliable. And so this is an example of an early calculator. Calculator consisting of, at that time, transistors were made out of germanium, 530 germanium transistors, 2300 diodes. Note that it's no longer, this computing machine, it no longer weighs in tons, it weighs a few tens of kilograms, and it doesn't consume kilowatts of power, it consumes only 90 watts of power. And instead of occupying an entire room, it occupies a fraction of your table, right? So a vast improvement occurred in terms of what one could do with the transistor. Things became a lot more smaller, would consume a lot less power, and were far more reliable. But you can still see that this calculator is not a very complex calculator. You can see that the number of components is not very high, but is still occupying a fraction of a table, a significant part of a table. And so the point is that even with the invention of the transistor, one could integrate, one could connect a lot more transistors, but it was still a problem. Let's go into that in a little bit more detail here. So as a summary, electronics started with the invention of the triode in 1906. 1948 was when the transistor was invented. And so after the vacuum tubes continued beyond 1948 also. It took some time for transistors to reach a maturity level and replace vacuum tubes. So almost like 40 to 50 years of vacuum tube era of electronics was there. And after 1948 invention of the transistors, the electronics gradually shifted to transistor-based electronics here. And initially it was based on bipolar transistors. And we also have a phrase called discrete circuits, and we'll explain in a minute what those discrete circuits really mean here. So a new era of electronics started after the invention of the transistor. So if you look at transistor, this is an example here. A transistor with three terminals, emitter, base, and collector, this black thing here. So the way circuits would be made using a transistor at that time, after the invention of the transistor, was you would take a transistor, pick it up in your hand, and you would put it on a board. Let's say this is a insulating board here, and you would place it at a particular point and solder it to that particular board. Similarly, these are resistors. The resistors would be soldered at a particular point, and it's not shown here. Underneath the board there are these wires which will connect the transistor to this resistor, or this transistor to this transistor here. And the wires were made by depositing metal on this on the board here, and so that's why this is called a printed circuit board. So anyway, the nature of fabrication of circuits was that each of these elements that you see here, a transistor or a resistor, existed as a discrete component, as a separate discrete component, and you would pick it up, you would place it at a certain point, and you would solder it, right? And that method of fabrication of circuits is a source of a problem. Why? Because if you look at the size of a transistor, you know, I picked up a transistor from our lab and placed it against a ruler, a scale, and you can see that the transistor is measuring about, let's say, roughly half a centimeter. And if you have a transistor which is, let's say, half a centimeter by half a centimeter, and you want to integrate lots of these transistors to make a complex circuit, you'll get into trouble. And at this point you may wonder, why do I want to integrate lots of transistors, and what do you mean by lots of transistors? How large? Well, let's look at as an analogy our brain. So this is a single neuron, and it can perform a simple computation, this neuron, and by itself can't do much. But then you get to the brain where we have billions of neurons. And when you have billions of neurons and you have, you know, these neurons are connected to each other, then we all know that the brain does interesting things. So the point is that similarly, a single transistor can do very little. It acts as a switch, or it can amplify a signal. By itself, it can do very little. But if you take lots of transistors, if you take lots of transistors, well, you could build a circuit, a computer in this case. Computer is also a circuit. You can build a circuit which can beat the world chess champion. So this is Kasparov, who was world chess champion at the time, playing against the IBM's computer Deep Blue, and this was the first time a machine beat a world chess champion. So the point is that once you take enough of these transistors and you integrate them, lots of them, and you interconnect them, then together, then they become a very powerful computational machine. And how large? Well, similarly, just like if you want to do something like this, well, you need to connect millions and billions of transistors. So let's see the difficulty then. So we said the transistor measures, let's say for simplicity, measures about half a centimeter by half centimeter. So this shows, for example, let's say a layout of a circuit. So we have one transistor here, another here, another here, and another here. So let's say each transistor measures half a centimeter by half centimeter. And the distance between two transistors, you have to leave some space for interconnection and all that. So let's say the distance is also half centimeter here, half centimeter here, half centimeter here, half centimeter here. Well, then each transistor is occupying an area of half centimeter here, let's say a quarter centimeter here and a quarter here. So 1 centimeter, and similarly 1 centimeter here. So one transistor is occupying an area of 1 centimeter square, which means that the density, transistor density, is 1 transistor per centimeter square. And let's say you want to build a circuit consisting of 1 million transistors. So 1 million transistors, which means that the area of your circuit is going to be 10 to the power 6 centimeters square, which means, let's say, if it's a square circuit, 10 to the power 3 centimeter into 10 to the power 3 centimeter, which basically means that 10 meters by 10 meters. So the whole circuit consisting of 1 million transistors would occupy a large room measuring 10 meters by 10 meters, which sort of shows that it becomes impractical. You cannot make circuits consisting of 1 million transistors using the methods that we have talked about. Is going to become very large, and not only large, it would weigh a lot, and it would become very slow. It would consume lots of power. So all those problems will occur, and therefore what we are saying is that with this particular transistor measuring 1 centimeter by 1 centimeter or half a centimeter by half a centimeter, you cannot make complex circuits. You cannot integrate hundreds of millions of transistors or hundreds of millions of transistors to make interesting circuits. Well, so we are showing here a transistor made on a, let's say, silicon chip, and there is an emitter, there is a base, and there is a collector that is there here. And so the transistor is actually very small. It measures in microns. Size is very small. It measures in microns. But The method of fabrication of transistor is such that I have to hold it in my hand, place it at a particular place, and solder it. So to pick, if I have something in microns, I can hardly see it. You can forget about holding it, placing it at a particular point, and soldering it. So because of the method of fabrication, what I need to do is, this transistor that you see here, I need to take this particular transistor and I need to make it large so that I can hold it in my hand and place it here and solder it. So even though it's very small, we need to package it to make it of a reasonable size so that we can handle it because of the way we fabricate circuits. So what we do is we attach these metal pads to our 3 terminals, emitter, base, and collector, and to these metal pads we have these wires that are attached that you see over here, and we take the whole thing and we take this whole piece of silicon and we place it in a package, and these wires that are there, they are attached to the pins of the package here, and that's how you get your transistor. That's how you get a transistor. So even though the actual transistor on the silicon is only a few microns, we package it in order to make it of the size of a centimeter, half a centimeter, let's say, so that we can hold it, place it, and make circuits. So if you want to do something interesting, we said, well, you have to integrate lots of transistors. But then if a transistor measures, if you package it like this, it measures a centimeter, then you cannot do it because it becomes impractical. The circuit becomes too large. So what happened was that these people that you see here, Jack Kilby was at Texas Instrument and Robert Noyce at Fairchild, what they proposed was a new method of making circuits, which we call as a monolithic integrated circuit. So both of them independently came up with this idea, and so the idea is that you don't make circuits by picking up a transistor and placing it on a board and soldering it. So the idea was that you take a piece of silicon, and let's say your circuit requires 16 transistors. So all those 16 transistors are made on the silicon IC, on the silicon chip piece of silicon that you see over here. All the 16 transistors are made over here. You don't make one single transistor and you package it and then you place it on a board. You make all 16 transistors on the silicon piece here. Now if you need a resistor, well, silicon is a semiconductor, you can make resistors out of silicon also. So you make the resistors, I'm not shown here, you make the resistors on the piece of silicon also. If you need a capacitor, well, capacitor is nothing but 2 metal plates with dielectric inside it. On silicon, you can grow silicon dioxide, which acts as a very good insulator. So you can make capacitors also on silicon. So the idea is that you don't make a component and you package it so that it exists as a discrete entity and then you place it on a board and solder it. The idea is you make all the components on silicon itself, all the transistors, all the resistors, and all the capacitors. And then you can interconnect them also. You can deposit, for example, aluminum. You can evaporate aluminum and deposit it selectively on a piece of silicon. So I can connect the base of this transistor to the collector here. I can do that. I can connect the emitter of this transistor and I can connect it with the collector of this particular one. So I can selectively interconnect them also. So the idea is you make the components on silicon, whether it's a transistor or a resistor or a capacitor, and you make the wires also on the piece of silicon. You deposit them, and thereby you make all the entire circuit on the piece of silicon itself. That's why it's called monolithic. Mono means single and lithos means stone. So the idea is that on a single piece of crystalline silicon, you're making all the components and you are integrating them, you're interconnecting them, you're making the entire circuit on the single piece of silicon. That's why we call it a monolithic integrated circuit here. And after you're done with, after you finished your fabrication and interconnection and all that, then what you can do is you can take this piece of silicon, put it inside a package and attach it to pins so that it exists as a component which you can use wherever you want. For example, if it's let's say a memory or an amplifier or whatever consisting of several components, you can then package it and then use it wherever you want. So this is the early patent, first patent that Jack Kilby filed for his idea. Note that he's writing, it is to be noted that all components of the circuit are integrated into the body of the semiconductor material. So what we are talking about is a new method of fabrication of circuits. You don't make a transistor, you don't make a resistor or a capacitor separately as a discrete component, and then you pick them up and you place it and you solder it. There is no picking of a transistor here. The transistor is made by N, P, N, and all those things that are there. Different regions, they are made by diffusing impurities, N-type and P-type. There's no picking of a component here. There's no picking of a resistor or a soldering of a resistor. This pick and place method of fabrication that you see here is not used here at all. Things are made on the piece of silicon and integrated on the piece of silicon, the wires and all that. So a new method of fabrication allowed very compact circuits to be made. As an example, this is an amplifier consisting of more than 20 transistors, about 10 resistors and a capacitor also. So the whole thing is fabricated on the piece of silicon. All the 20 transistors and 10 resistors and capacitor, all of them are fabricated, and the interconnections between them, wires, everything is made on the piece of silicon. And therefore, because you're making it on a piece of silicon, and transistor is inherently very small in microns, so even if you have 20 transistors and 10 resistors and all that, the whole thing measures only in millimeters or even smaller, the whole piece of silicon. Now after that, what you can do is you can package it, and the package is not going to be larger because the silicon piece is still very small, right? So this is the size that we showed of a single transistor, and if you took a circuit of 20 transistors and 10 resistors and a capacitor and you put it in a package, this size is still very small here. You can see the package size is less than a centimeter still. So the invention of the integrated circuits made it possible to build very complex circuits consisting of lots of transistors, and still the size remains very, very small. Size remains very, very small, and all the other advantages came. Advantages of reliability, cost, and other things that came with this new method of fabrication of circuits here. So the density, meaning number of transistors per centimeter square, one could pack lots of transistors in a small area. So what happened was then, 1948 transistor was invented. 1958 is the invention of the integrated circuits, and a new era of electronics began, which we call as an era of integrated circuits based electronics here. So most of the time, most of the components would be integrated in the form of ICs, and the ICs would, of course, then people would take several ICs together, and one would use pick and place method to construct even larger systems. Okay, so a new era of electronics started with bipolar integrated circuits. At about the same time as the invention of the IC, a new transistor was invented called MOSFET, metal oxide semiconductor field effect transistor. Now this transistor was, compared to a bipolar transistor, simpler to fabricate, occupied less area also, which means that you could, in a given area, you could pack, or you could fabricate a lot more MOSFETs and interconnect them as compared to bipolar transistors. So electronics became dominated by, even though bipolar transistors are still used, became dominated by MOSFETs here. And another thing happened in 1971, a microprocessor was invented. In the last lecture, we talked about programmable digital hardware. And once you have a programmable hardware device, it opens up that particular field to a lot more people. Everybody cannot design a microprocessor, but everybody can write a software, or most people can write a software and program the hardware to do what you want. And so after 1971, I would say a new era of electronics started, where microprocessors and memories, when you want to program something, when you're talking about software, you need memories also. So a new era of electronics started, which was dominated by MOS integrated circuits, and where microprocessors and memories played a very, very important role. And another thing that happened was, as I said, if you want to make complex circuits, you need to interconnect, or circuits of the order of, let's say, hundreds of millions of transistors. Without the circuits becoming too large, you need to have transistors which are very, very small. So another thing that happened from over the years that has happened is that the transistor size has shrunk almost like every year and a half or 2 years. the transistor size, a new technology comes to the market, where the ability to pack number of transistors doubles. And so we started with almost like in 1958 or so, we talked about 1 transistor per centimeter square kind of a density. We are now at a stage where we can pack 100 million transistors in 1 millimeter square here, and the transistor size that you see here is a few nanometers. And so when you can build circuits with almost 1 billion transistors, now you can do lots of interesting things, and that's why we are now in an era of machine or artificial intelligence. And electronics has reached a stage where you can build not only 1 billion transistor integrated circuit, but even 1 trillion transistor integrated circuits. People have even packed, and those circuits, for example, 1 trillion transistor circuit measures only about let's say 10 centimeter by 10 centimeter. So you can see the power of this new method of fabrication of circuits called the IC, the monolithic integration of circuits here. So as a summary, electronics began with the invention of the triode. It was a revolutionary device. One could do many new things with the triode, but the ability to integrate lots of components and do something interesting was limited. And this example of early computer shows this whole thing occupying an entire room. With the invention of the transistor, things became much better. Transistor was smaller, consumed less power, far more reliable. What occupied an entire room now occupied a tabletop. But even with the transistor, as we discussed, integration was limited. You could not integrate transistor 1 million transistors and make circuits using the method of fabrication of circuits which was based on pick and place kind of a method here. Electronics had to wait for the invention of the integrated circuits, a new method of fabrication of circuits. And once the IC was invented, electronics really took off. Now one could pack lots of transistors and interconnect them and make complex circuits. And so what I would like to say is that for the modern day electronics, transistor is a necessary condition, and in the language of maths, IC is then the sufficient condition. So necessary and sufficient, the two together are responsible for the electronics that we see today. So while the importance of transistor was realized very early, transistor was invented end of 1947, or let's say beginning of 1948, and almost like 8 years later it was honored with a Nobel Prize. The importance of integrated circuits was realized much later, but it was honored with the Nobel Prize in the year 2000. All right, so this sort of captures as to how electronics started and how it has evolved over the years. And we are of course now in an era of integrated circuits, very complex integrated circuits. People are talking about integrated circuits with billions and even trillions of transistors. And so from next lecture onwards, we'll start looking at properties of circuits, how to analyze them, how to build them. All right, so let's stop here.